course corrections, this is the time to lock it in. After the midterm, you'll see that the p-sets drop off so that you can have more time for your, there's one more p-set down here, but we're going to try to have less significant p-sets so you can start transitioning to work on the projects. And we're going to try to have at least one sort of face-to-face check-in with you and a few chances for you to just submit very short blurbs to just make sure you are making progress and not stuck on programming things. You're stuck on the important things. Okay, so start thinking about what you might want to do for project proposals. A few of you have already emailed me or the staff with some, here's some rough idea about what I'm thinking. How does this sound? That's a great idea. I think that's if you have anything that you just be thinking about, feel free to reach out to us before the project proposal. But certainly the project proposal is a chance for us to give you specific feedback on your ideas. Good. Okay. So today we're going to transition to talking about, we talked a lot about Lyapunov functions last time. Today we're going to talk about algorithms for Lyapunov functions. The feedback we got from your last, your last p-set and even the ones that are coming in this time, everybody still wants more intuition and still more connectivity. So I'm going to do my best here to give you that, and I wanted also give you plenty of chances to ask questions. So I'm going to give you the quick overview again of where we are and how it relates, and then I'll take a breath. And if you have questions about how these things connect together, by all means, it's a great time to ask. Okay, so what are Lyapunov functions in the grand scheme of why you care about control? That's what I want to sort of motivate again here. Right, we've talked about optimal control through the lens of dynamic programming and the Bellman equation, right, where we take our long-term objective, which is described as some additive cost. I'll even be careful here. Okay. We have some long-term objective subject to the dynamics of the plant. And through the amazing results in dynamic programming, we turn this long-term objective into the search for a particular function, the cost-to-go function, right, which has the beautiful Bellman equation. Right? If you can find a j that satisfies this equation, then you've changed the long-term optimization of trying to find an entire sequence of command inputs u into a one-step optimization saying what I really need to do is optimize my one-step cost plus the cost to go. Okay. For navigation problems, we had, for our grid world type problems, that cost to go function had a very physical interpretation. Right? We took our one-step cost, where this is the goal, this is the obstacle, and through the value iteration dynamic programming update, we backed out that one-step cost into the cost-to-go function and got ourselves a map, roughly, so that at every initial state, this cost-to-go function tells me what direction should I move to go downhill. Right? To go downhill on the cost to go means I'm making progress on my task, and it will eventually, in the simple case of having a goal in state space, this is going to take me directly. If I just forget about the long term and just try to go downhill on my cost to go function, then I will get to the goal, and I'll do it optimally. Okay? I wanted you to think last time, right, about solving this equation. In the continuous time, it's a partial differential equation, right? So in the continuous time, this looks like solving a partial differential equation. This is you know, the result of the continuous time version of that, we're saying that I want to find some j such that when I'm taking the optimal actions, I'm going downhill at some rate, which is the instantaneous cost. Right? And this, solving that partial differential equation, especially since u depends also on j, right? There's hidden complexity inside here. That I don't want that to look too simple. Okay, but solving for j, solving this partial differential equation that has you know, discontinuities in it and whatever, that's a hard problem. That's a really, really hard problem. And what we've done with Lyapunov, what I want you to see is we've changed this big, hard optimization problem into a different optimization problem, where we're going to try to find a function v, and instead of trying to say it's exactly, putting some, you know, exact equality on the derivative at all places in state, we're just going to say relax this to a much simpler condition. I want to find any v that's negative for all x. dv dt is negative for all x. Positive v, negative for all x. All the conditions we wrote down last time, okay? My claim was that, you know, well, I think it's clear that many more functions can satisfy this condition than this. There's a unique solution to the cost to go function, but there are many Lyapunov functions that can certify the Lyapunov conditions for any particular control system. Okay. And my promise to you was that this was going to make a difference computationally too, that somehow having these conditions was going to give us more powerful algorithms that could solve harder problems because they're only trying to solve these weaker conditions. Right? So today I'm going to try to make good on that promise and give you some of those algorithms and see why that makes such a big difference, changing that equality to an inequality. Okay. You know, there are variations of this. When I write it like this, I can't help but sort of say, well, why less than or equal to 0? Is it the less than or equal that's important, or is it the 0 that's important, right? I mean, it's really the inequality that's important. There's versions of this where you can say, you know, I want to say it's like less than or equal to negative L of x u, or let me just even say negative L of x, since we don't have u in this right now, but I could have this saying I want it to go less than some rate or some cost. That's also going to be a way to think about something in between control cost to go functions and Lyapunov functions. Okay, and we'll work on that, I promise, soon. Does that level of intuition make sense? This promise that we're making the problem easier by asking not for optimality, but for sufficiency, just to say I'm going to get to the goal. Right, so for instance, in this picture, if I could find a Lyapunov function for the grid world, right, or for some complicated navigation problem, this would be a valid Lyapunov function. The cost to go is a valid Lyapunov function as long as my costs are positive. But it's not the only one. If I can find any Lyapunov function, then it will tell me, again, it solves the long-term optimization problem in the sense that I know, I have a guarantee if I've satisfied the Lyapunov conditions, that if I just look at my current Lyapunov function and try to go downhill, I will get to the goal. That's what it tells me. It doesn't say anything about optimality. You might meander a little bit on your way there. But if you can find a Lyapunov function, it will still get you to the goal, just not optimally. So what we're giving up on, we're still accomplishing the task, but we're giving up on optimality. And that's what makes things change complexity classes, in some sense. I mixed continuous and discrete here. The same thing's true in discrete. There's a Lyapunov, there's a Lyapunov function. You can do Lyapunov analysis in discrete time. You just say that V has to go down on every step of the algorithm, right? All those things match. But because I treated Lyapunov as a continuous time, this time I wanted to write it as dv dt here, okay? All right. So, just to make that point even more, right? So imagine I have some interesting control problem, and I just happen to know the optimal cost to go, right? Like maybe I know exactly how to solve for j star of x, right? And it's like a polynomial of degree, I don't know, I'm just making this up, right? Just to be clear, this is not a precise statement. I'm just saying, 4,230 or something like this, okay? So I've just got a ridiculously complicated function that is the optimal solution to like my control problem, if it's even a pendulum swinging up or atlas balancing, okay? It could be that oftentimes the cost to go is a very complex function, right? But it can also be that there's a v of x that satisfies the Lyapunov conditions, of degree, I don't know, 4, right? That could give up on optimality, but still guarantee that my pendulum's going to get to the top, right? So it's partly the inequality that matters, but it's also the fact that I can search over intentionally simpler functions that could not possibly satisfy the equality everywhere, but they can satisfy the inequality everywhere. And that's a common thing. Like the energy of the pendulum is a pretty simple function. Integrating the dynamics of the pendulum as a function of time is a very complicated function, right? But the energy is a simple function that certifies that you get to the bottom. Okay, so that's the big idea here, is that by saying I don't have to be optimal, I just want to be as sufficient, you can find much simpler functions that guarantee things for even very complicated systems. And once you get into the land of approximation, where you just can't satisfy this exactly, you're using a neural network or something like this, then I think being able to say statements, you already have given up on that strict equality. So it makes sense to make it a one-sided, and then you still have some guarantees. Right, so for the navigation type problems, it looks like this, and then for the pendulum type problems, it's backing out the dynamics, right? So we want to find something that plays the same role as this. It provides sort of a map that gets me to the goal, but I want to do it easier. I don't want to do as much work. I want to find low complexity functions that still guarantee I get to the top. Okay? Questions on that? Are people with that idea? Thumbs up, thumbs down, thumbs in the middle? Okay, good. All right, so let me give you a preview of the type of things that we're going to do next, okay? So this is a very simple optimization. Oh, sorry, I scrolled. I should have not scrolled while I said the word simple, but right, that will prove that the pendulum is stable globally with a numerical algorithm. This is a proof that comes out of a numerical algorithm, okay? And long story short, if I run this, it finishes instantly, okay? And it will produce a certificate that says that my pendulum, this one is getting to the bottom because I didn't have any control input. So this is just proving that the pendulum goes to the bottom, okay? But it's formulating a search for Lyapunov function. There's two curves, there's two plots here. One of them is the energy landscape, just that I knew from physics. And the other one is the Lyapunov function discovered by the algorithms that we're going to talk about today. And you can't even barely see the difference, okay? We don't have to be, I mean, last time someone asked, they said, you're coming up, you're just conjuring these Lyapunov functions out of nowhere. That's not very satisfying, right? Where did they come from? And I'm saying that we didn't have to be clever and come up with energy. We can just put the equations of the system in, say certify that I get to the bottom, and it's going to recover energy in this case. Actually, it does a little bit better. So this small difference between the energy function and the Lyapunov function it finds is not some numerical artifact. It's actually done something smarter than what we did with energy. Remember how we had to play the extra games with the energy argument, with the LaSalle invariance principle, because E dot was actually 0 every time it paused and turned around. And so we had to do extra work in our proofs to actually say that it gets to the bottom? Well, it turns out there's a small tweak on the energy function where you don't need that. And the algorithm finds that. Okay, so it just adds a couple small terms that makes it unnecessary to do Lassalle's invariance principle in order to use the energy-like function to prove. So it's done better than what I did from physics. Okay, and it's ironic that you guys are all watching neural networks train a pendulum right now, right? And that's a frustrating experience sometimes. I mean, it's powerful. It can go a long way, but there's hyperparameters to tune, and there's things to get right, and it takes a long time. And this is a different class of algorithms. They won't solve Go, right? They can't play the game of Go with this. But for systems, mechanical systems in particular, these have no parameters to tune or whatever. These are the stuff of convex optimization as opposed to the non-convex optimization, and they have very satisfying solutions. And if it didn't work, you have a bug, and you can find it. So I find these a lot more enjoyable to work on. I have been training networks at home. My energy bill is like probably through the roof this year. My GPU, actually my router, I think, got overheated by my GPU, the other day. And it's just, I just press enter and it's done. Or if it's not, I had a bug and I can fix it. It's a totally different experience. So I hope you guys get excited about these algorithms, and we'll push them farther and farther towards the great things that we do with neural networks. Okay, so I want to work through that example. We'll do it in a couple of phases. And I introduce the tools that you'll need for it. I mean, a lot of these tools are based on convex optimization. Alex gave a crash course last night. And maybe if you didn't attend and it's recorded, if you might find that by the end of the lecture you wish you had attended last night. But I'm going to try to walk that balance. I'll bring people in who have a basic understanding, and if you want more, Alex, I would highly recommend Alex's material. But here's I think the core idea doesn't require expertise in convex optimization for sure. We're going to become powerful users of convex optimization. Okay, here's the core idea in computing these Lyapunov functions, in that example and in other examples we'll do. I think the core idea is we're going to parameterize the Lyapunov function. So for instance, if I start with x dot as f of x, right, Lyapunov so far is about the closed loop dynamics, not the open loop. We'll address that later. Then what I'm going to do is I'm going to formulate a search over possible Lyapunov candidates, v of x, and the same way we parameterized function approximators for the cost to go, we'll parameterize function approximators for Lyapunov functions. Okay, a natural class is the linear function approximators. Same thing we said for cost to go, okay, which again I like to write in vector form. And the strong advantage of using these linear function approximators is we're going to be able to satisfy the Lyapunov conditions, by formulating convex programs to find alpha. Okay, and it's not just alpha to, for v, but also we have to sort of find alpha that satisfies the derivative equations too, right? We want v dot of x to be less than or equal to 0, also, right? So v dot of x in this setting is partial phi. Let me write it like this: partial v, partial x, f of x. If I'm considering function approximators of this class, it's important that these linear function approximators are still linear function approximators when I take the gradient, right? This would still be alpha transpose d phi dx f of x. Okay. And again, this looks very restrictive. It's not a deep network, but it is, you know, you can put arbitrary complexity in here. And it's going to go a long way. Okay. And then we're going to use, you know, optimization to try to find alphas that satisfy, you know, this being greater than or equal to 0 and this being less than or equal to 0. That's the first, you know, basic way to think about it. There's a lot of details that follow from that. But that's the most important thing. Okay, so there's a version that is that you have all the pieces for already. Do you remember your problem set where you did a linear program to satisfy the Bellman equation, right? And you pushed up from below, so you actually did do roughly this. You pushed up from below to say that the cost to go was everywhere less than or equal to, right? And you did that at a bunch of sample points. Okay, so the first thing you could say when you see this, we could do a sample-based algorithm. Where we could just start saying, I would like these conditions to be satisfied at a bunch of different x's, right? So for all xi in some data set, okay, I'd like, you know, v of xi to be greater than or equal to 0, v dot of xi less than or equal to 0. Given an x, if I put an xi in here, then this just becomes, if I can evaluate the function at that x, this just becomes a vector, right? It's a bunch of numbers. There's no hardness there. This whole thing just becomes a vector, which is just a bunch of numbers, right? Okay. So this constraint is linear in alpha, and this constraint is linear in alpha. So you can write a linear program that just says, you know, find me an alpha such that for all, so I'll write it for all I, you know, v of xi greater than or equal to 0. That's a linear constraint. V dot of xi less than or equal to 0 is also a linear constraint. In practice, it's often beneficial to not just to actually put an objective so it can pick, because there's so many choices for v here. I try to put one in that says, you know, among the many v's you might pick, try to pick one that goes downhill about at the rate 1, which would be like the time to go, cost to go. But that's just an objective. These are the hard constraints. You already have all the tools to do it. You could type that in and do that. I've typed that in. I forgot to convert it to Python, so I'm going to run it the C++ version, but it's basically exactly the same thing. And guess what? When you ask the pendulum, given those equations, right? Because again, the f of x for the pendulum is nonlinear, but if I evaluate it at a particular xi, it's just data in the program, so that's still a linear program. And I say, find me an alpha that satisfies these conditions, that v of 0 is 0, that I put another sort of simple thing in saying that maybe v of 1 should be about 1, just to give it some scaling, okay? But those are just details. And I've printed out here the true energy of the pendulum and the Lyapunov function that it finds. And they're pretty close, okay? So I get a, the 4.095 or whatever, it comes up the way it should, and then the q dot squared term is smaller than in the energy function, but it's spread that out and put this extra term in here, which again certifies less than or equal to 0. It gets me to the goal, not just, or less than 0, not just less than or equal to. Okay, so that's a perfectly reasonable algorithm that gets you started. It's easier than the cost to go because there's a huge number of functions that can satisfy that constraint, those constraints. And it does the job. Yes?
I may be misunderstanding it, but so in the sample-based algorithm, you're finding the sort of sample data that you're picking across the full space. Is there any trick to interpolating between them, or is generally just a standard like linear interpolation work out?
So I am not doing any interpolation here. I'm only evaluating the function and its derivative at a bunch of sample points. So this happened in the simple example. I could exhaustively sample enough that it gave the true energy function. So the question, in case anybody didn't hear, was about whether there's some smart interpolation going on. The limitation of this algorithm, and what we're going to do much better with in what follows, is that this doesn't actually certify the Lyapunov conditions for all x. This only says the Lyapunov condition is correct at those finite sample points. So the next round of work is going to be to think about how do we take this from, for all I at finite sample points and actually make a claim that it is good for all x, independent of sampling. Yes?
How do you actually come up with these functions?
How do I come up with these functions? Okay. Well, I'll give you a specific example. In fact, let me give you show you exactly what I came up with for the pendulum. I meant to write that down. I forgot. How do I come up with the functions? Again, I just need to parameterize a sufficiently rich set of basis functions. You can over-parameterize. That's not a big deal. You just need to have sort of enough richness, right? So for the pendulum, both in the first algorithm I ran and in the numerical one I ran in C++, right, I have suggestions coming from the dynamics, right? So just to So I've got sine thetas kicking around. I've got theta dots kicking around. I know that the energy has like theta dot squared kicking around. Okay, so the basis function I chose was a vector. I've got a bunch of bases, right? So I put 1 in there in case there's a constant term. Okay, I put sine of theta in there, sine of theta in there, theta dot. But then I also put in cosine squared theta. I didn't bother with sine squared theta, because if I have 1 and cosine squared theta, then I could do the sine squared theta. So I left that one out. But every other permutation up to degree 2, I did put in there. This is just the generic basis that you would get if you said I wanted the generation of all monomials, the one term of a polynomial, where I have just up to degree 2 of these combinations of these simple basis functions. Pretend the board was a little taller than it is, okay? That was my palette. And then I searched for alpha as that was able to mix or match those components. If I had been less sure, maybe I could have gone on. I mean, I think using sine theta, cosine theta is a recipe that's going to work for lots of robots. If I didn't know what the degree could have been, I might have extended that up to 3rd power or something like this. But that's a very natural basis that comes right out of thinking about the equations. Yes?
So is that theta dot cosine theta?
It's a small dot. Yes. Yeah, I explicitly don't have theta and cosine theta. it wouldn't be terrible to do it in this particular algorithm, but in future algorithms it would be more painful. Yes?
Is there a reason you chose not to include theta double dot?
Good. So think about this as the question was, why not theta double dot? So in this case, it's theta dot and theta double dot on this side is f of x on this side. So the MGL, whatever, is over here. My Lyapunov conditions, my partial v partial x f of x here, there's no theta double dots that are going to appear on this side in my Lyapunov conditions. So I don't expect to have theta double dot kicking around. Great question. Okay, so that's a perfectly good basis for mechanical systems of one variable, that have a rotary joint. I guess that's only a pendulum. Okay, but it will work for more interesting systems too. That's a recipe that we'll continue to give. All right, so what I want to think about with you now is how do I take that basic idea, which does work in low dimensions because I could sample enough, but make it work. First of all, if you just care about mathematical, having a certificate, an actual proof, then we want to address for all x, even in the low dimensional case. If you don't care at all about the proof, but you just want it to scale to higher dimensions, you also want to get rid of the sampling because that sampling isn't going to scale. You can't sample densely in high dimensional problems, okay? So for both reasons, we're going to try to do better and do something for all x. So let me get there, Here's an idea. This comes up a lot in various applications of neural networks and other function approximators. What if I parameterize it to v in a way that it just, I want v to be positive everywhere. Why don't I just parameterize v so it can't be negative, right? So for instance, instead of choosing v of x is, some arbitrary functions, what if I did, I'll write it like this first. What if I just put a squared there, right? You give me a whole bag of functions, and I'll just make sure I take a square of all of them. And this thing can't be negative, right? So this thing, if I keep alpha greater than 0, this thing can't, be negative. Okay, so that's a pretty good idea. But we want to achieve the same thing for v dot, right? So I don't get to necessarily pick, this is going to have the dynamics come into it. So even though I could do this, let me actually right now say there's a generalization of this idea that's going to be important. This is just a combination of a bunch of nonlinear basis functions, right, which I wrote as alpha transpose phi of x before. What's the full form of this? What I want to write now is phi of x transpose times some matrix that has alpha 1, 1. I'll call it, I don't know, G, because I don't have the big alpha to work with here, okay? This is the matrix form of that. And what I'd like to do, the equivalent of the alpha just being greater than or equal to 0, I'd like G to be positive definite. This similarly for arbitrary functions phi, if it's multiplied by a quadratic, it's in a quadratic form here where G is positive definite, gives me things that can only be greater than or equal to 0. Positive semi-definite gives me greater than or equal to 0. Yeah. Okay, so that's good. Can we do optimization over this, these forms, right? And this is where we'll start digging a little farther into convex optimization, right? So constraints, this is clearly a linear constraint in the original parameters. The parameter, this is a non-linear constraint on the coefficients of the matrix, the positive definite. If you take the eigenvalues of a matrix, you get it's a complicated nonlinear function. But it turns out this is still a convex constraint on the, it's not linear, but it's convex constraint on the coefficients of the matrix. Okay, so optimization over constraints that have positive definite matrices is a convex optimization. Now, there's notes in the book. There's a great tutorial from last night, and actually Alex even has he gave a whole IAP course on convex optimization. So if you want the 6 lecture version or something, then those are available too, where you can go through each of them. Okay, but what I want you to have in your head here is there's multiple types of optimization problems, right? We've talked about optimization problems where we had decision variables x and objectives f of x that were convex, and the attribute is that when you have a convex optimization, you can have a global optimization that's guaranteed to find the minima, and satisfying algorithms that will converge quickly to that minima, versus non-convex optimization. When you're working with neural networks or other things, you're more squarely in the land of objective functions potentially that could have many local minima, and your solver might get stuck, and you might have to play more games to find the minima, right? This is actually this is a constraint, not an objective, but the picture I want you to have in your head here is that when you have convex objectives and convex constraints, then you have good algorithms for finding the global optima of the problem fast. There are other, it's more than that. You could take a whole course or two on convex optimization. But for our purposes, we have a modeling power, which is that I can write optimizations where I have constraints on the matrix. Okay. Moreover, I can, if I have the decision variables are the elements of the matrix. So for instance, if I wanted to, something very simple, if I were to just say minimize over alpha subject, let's say alpha subject to alpha 0, 0, 1 greater than or equal to 0. Okay, that's about the simplest constraint I could give. This is a semi-definite program. Because it has a constraint of the form of a positive definite matrix. But I can write the constraint, and I can also write any convex objectives or other constraints on the elements of that matrix. So in this case, this program, if I run it with a convex optimization solver, will return alpha is 0, or it's 1 to the minus e to the minus 6 or something, right? Whatever the tolerance of the solver is, something just barely above 0. We're going to use this. We're going to want to be able to dig in a little bit, write a constraint on the matrix, but also write elements of the decision variables of that matrix in other constraints. There's some also good questions in the feedback about Drake and about running it on different platforms. Someone said it doesn't run on Mac, but it definitely runs on Mac. I run it on Mac here all the time. The deep note And the general binaries, for instance, that you can download if you install Drake just from binary, it has packaged inside it all of the best open source solvers for convex optimization problems that we've wrapped, right? So we package those up and send them along with it. You get those for free on DeepNote, thanks to the open source community. There are more powerful solvers that are very expensive if you're not an academic. They're free if you are an academic. I'm actually working to try to have those companies allow me to distribute the binaries with Drake so that you could just apply a license file. But if you start making big convex optimization problems and you want the stronger solvers, right now you build from source. Okay, so Gurobi, Mosec, if you know these are the more powerful solvers. I'm working very hard to get those so you can get them on DeepNote and everything too. Okay, but the difference between a rudimentary convex solver and a large-scale, high-powered one is dramatic. Okay, it's also expensive. Right? They charge you like per core. You know, it's like really you're gonna okay. To get you in academia, and then you send you off and you ask your company for a license. Okay, so V of x, we can just by design, by parameterization, say, I'd like to search only over the functions that are positive, you know, that I'll parameterize it like this, and I'll put a positive definite constraint here. How do I handle V dot of x? V dot of x, I don't get to just purely design. I have to deal with whatever the dynamics brought to the table too, right? So how do I parameterize that in something that looks like, you know, that's guaranteed to be negative, right? Okay, we're gonna to solve that resoundingly, but let me show you first how it works in linear systems, okay? Because that's where it all begins. Okay, so for linear systems, I have x dot equals a of x. I already, in my very simple one-dimensional example, used a quadratic Lyapunov function for a linear system, and in general, we're going to look for quadratic Lyapunov functions. Okay. I mentioned before why that is, right? But let me just, it's not a coincidence, right? Let me just, you know that if you have x dot equals a of x, the solution to that is an exponential, matrix exponential, right? It's x0 e to the at, right? Or I should put it this way for the matrix case, sorry. E to the at x0. So if you think about it as this Lyapunov function is solving something, or a caustic O function that's solving something like the integral of a quadratic cost, for instance, then that's going to give me something that looks like, you know, the integral of e to the at x0 q e to the at x0 dt. And I can actually mess that around since these things are linear. I can write that as Right? That's just where it comes from. It's not arbitrary, right? The solutions to linear differential equations are these quadratic forms. Okay, when you have a quadratic cost, you get something of that form. Okay, so let's work on certifying the conditions of that Lyapunov function. Right, so V dot in the linear system case, again, we have to get a little comfortable with taking matrix derivatives, but a partial of V partial x times f of x, I get something that looks like this for my first term, and then my other term I get x transpose A transpose P of x. And I want this function to be less than or equal to 0 for all x. But we in quadratic forms, we know how to do that, right? We can forget about it. We don't have to sample x. Right? This is the magic, right? This is what's it's a simple step on the board, but this is where the magic happens, right? I don't have to think about x actually here. The conditions that certify this for all x are just that this is a negative definite matrix. In this one, I used the definiteness of a function. This one, I used it as the definiteness of a matrix. If I just worry about the coefficients, there's only n by n coefficients of this matrix. If they satisfy the finite number of conditions that specify these, the positivity or negativity of this matrix, then I've certified this for all x with no sampling. Right? That's pretty good. You should be asking, okay, but how's he going to do that for the nonlinear systems, right? But still, that's the basic idea. So, so now it's clear that I could write, I could certify, if you give me A of x, and you ask me, is it stable? Well, frankly, I should probably just take the eigenvalues and be done. This is a circuitous way to solve for the stability of A. But it's more powerful. So you're gonna believe me on that in a second, I think. But I could, if I was being stubborn about it, say I'm going to use convex optimization to tell you whether A is stable or not. And I'm going to do it like this. I'm going to say I'm going to find you a P that's parameterized in such a way I won't write all the coefficients of P. I'll just write P11, P12, and then I'll use the P12 again here, right? So I'll just make sure it's symmetric by its parameterization, okay, such that P is greater than or equal to 0, and normally we write it the other way, like this. You put this into your solver, you ask it to find you a P. A is just data in that case, right? And if it gives you an answer, then your system is stable, and it's proven stable by the Lyapunov function x transpose P of x for all x, no sampling. Okay? Are people with me on that? Oh, not as many thumbs. Ask questions. Yes?
What makes this formulation a convex optimization?
Okay. So I see you have to understand, I always feel very conflicted about how much to talk about convex optimization. There's no secrets. There's no secrets. It's just a matter of what I focus on. Okay? But what I want you to say is that there's a way to call a solver saying, here's some a parameterized matrix. I want that matrix to be, here's a constraint. That matrix is positive definite, right? So, okay, why is this a convex optimization? That's a great question, right? Good. Oh, great question. That one we should definitely do. Okay, so how do I tell the solver about that? Normally, the solvers actually will let you just spell something like this too. But the reason that's okay and the reason that's just a semi-definite program is that what you can actually write that behind the scenes, what the solver is doing is it's going to find P1 and P2 both symmetric. Let me write it like this. Okay, such that P is greater than or equal to 0, P2, let's say, is less than or equal to 0, or let me even, I'll just be super pedantic here. I'll say that's equal to this, and then A transpose P plus PA equals negative P2. And the elements of this, that's just a bunch of constraints saying that, you know, A times A11 P11 plus A12 P12, you know, whatever, plus this equals P00. You know what I mean? I put my 2's in the wrong place here. I got 1, 1. Right, that's just a bunch of linear constraints on the elements of that matrix. Thank you for asking that. That's a good thing to highlight. Okay. So even if my modeling power is only to say I can make a particular matrix with decision variables greater than or equal to 0, that allows you to make linear combinations. These are called the linear matrix inequalities, still in the class of semi-definite programs. Okay, so this is still a semi-definite program. Yes?
So this works for linear time invariant systems or also time invariant?
Great. So the question was, is this restricted to linear time invariant systems, which is what I've written here. This is time invariant. If this was A of t, for instance, then that's a linear time varying system. We'll have versions for that too, I promise. Yeah. The simple recipe I put here is for time invariant only. Yes?
So if, maybe I missed it, but if A is like constrained by the dynamics of the system.
It is the dynamics of the system.
A is the dynamics of
Yep.
the system. But here we're saying A transpose P plus PA less than 0, we can find, if we find an A that satisfies.
A is given here. It's data. I'm only searching over P.
Oh, okay.
Good question, right? A is given to me by the world. That's my robot. And I have to find a P that works with it. Yes?
Does this give us anything beyond what we already know about linear systems?
Haha. Does this give us anything that beyond what I already knew? I should just take the eigenvalues if I wanted to solve this. Right. Here's a version. I anticipated that question and prepared a very impressive generalization. Let's do robust stability. Here's something you don't out of the box get to do with eigenvalues. Okay? So imagine now that I don't know what A is. A is, I know something about A. I know that its variables are, its values take some, you know, in some range, but I'm not certain about A. There's some uncertainty about the values of A. So let's say that A, I'll write it as, there's a bunch of different ways to talk about I'm not sure what A is, but one way to do it would be as a linear combination of other A's. So if you think about in the parameters of A space, if I have like, it might be this A, it might be this A, it might be this A. You know, there's a bunch of A's it might be, and actually it could be anything, any A's in those, you know, that's a way to parameterize. I'm not sure exactly about the values of A, but they're restricted to some range. Okay, so A is a linear combination of other A's. Consider this program now. Find P such that P is greater than or equal to 0. So my Lyapunov function is still positive definite and radially unbounded if you're playing along. And then for all I, I'd like to say that you know, PAI plus AI transpose P is less than or equal to 0. That's just more semi-definite constraints. If I can find a P that certifies this, then actually, even though that's a finite number of constraints just at the boundaries, it actually guarantees that every A in that set is stable. Robust stability via, this would be called a common Lyapunov function. It's one Lyapunov function that certifies many possible dynamical systems. You can't do that out of the box with eigenvalues. Okay, you can do that here. And how do I convince you that that's true? If this is true for all of the individual AIs, then for any particular A, right? We said A was this. So if this is true, then also it's true that yeah, if I were to use this equation in here, factor it out, right? Then this whole thing for this, for all betas, I should have been careful and written equals 1, and sum of beta I equals 1. Sorry, I was sloppy about that. Okay, it's a convex combination of the different A's. If I then write the dynamics of any A in that set, right, then I still have a proof that that's going downhill. The B dot is negative. Now this is actually super interesting, and we could go off on this, but if A is stable, I'm guaranteed that there exists many P's. Okay? This does not enjoy as strong of a statement. It could be that every A in this set is stable, but I couldn't prove it's stable by a common Lyapunov function. So, but if I find a P for this problem, then I have certified. You see, the direction is one, the implication is one way. If you find a P, a common Lyapunov function, then it certifies stability. But it's not clear that for an arbitrary set of stable things that you can definitely find a quadratic P. Yes?
So, this might be a ridiculous question, but if you move A for example, if that was a non-convex set now, does this certify stability for everything in the convex set, or the not, does convexity matter?
Great question. Okay. So let's say I moved A4 up, and I have a non-convex set, right? So if I certify these conditions, then it would certify everything here. That's true, but it would only be it would actually be certifying the convex hull. Okay, so if there was a matrix in here that was unstable, then I would not be able to certify it with this recipe. But if I do certify with this recipe, it certainly certifies. It's again the one-way implication. Right, so it would be, you'd be asking it to certify the convex hull of that. You don't have to call a convex hull routine or whatever. This would just, it happens from the way I've written this. Great question. Okay, a couple big ideas here, right? We got for all x, by thinking about not the entire v's, but just the positive definite form of v's. Okay, and the way we related our derivative equation, which now has the dynamics in it, was by, thank you for asking it, but it was by this coefficient matching here, right? We invented a second positive form, and we made sure it matched v dot at all of the coefficients of the matrix, not all of the x's, all the coefficients of the matrix, the finite coefficients of the matrix. Do you have okay? All right, so how do we now generalize this? Did you have a question or no?
Yes.
Oh, okay, I'm sorry.
Can we go back to
This one?
no? Is it because like we have a linear system that if we can like show like it's stable like locally that implies like global stability, or is there like any other conditions?
I hope this, so your question was, if we show it stable locally, does that imply something globally?
Yeah.
I hope that this picture is in the space of parameters, you know, A11, A12, A13. It's not in X. This is just the way I parameterize the A matrix. Everything I've talked about here is a global analysis of the stability. Does that answer the question?
Yeah.
Okay, great. Yes, thank you for asking. Right, so that is not a region in X. That is a region in the coefficients of A.
So like we're proving for all X.
And we're always proving for all X in this case. Okay, so your mind's running. So how do I then generalize this idea, this trick of working with quadratic forms to the nonlinear case? Well, I don't know, actually that's pretty good. I'll leave that one there. Let's, instead of parameterizing this, remember, we're going to switch to parameterizing like this. Now, v dot, partial v partial x, f of x, is going to look like, using that same set of operations, it's going to look like partial phi partial x, f of x, plus the transpose of that, f of x transpose and what I want to say, big question mark here, is can I make that something like phi of x transpose p2 of x? Can I do something like coefficient matching so that if I just say if p2 is also positive definite, and I can make those coefficients match across, then I can generalize this through my phi of x, right, to nonlinear systems and nonlinear Lyapunov functions. The question is, does this, you know, x versus this thing, I mean, it's not clear that we've stayed in, you know, partial phi of x, partial phi partial x, f of x may or may not be representable. It might be part of your basis set or it might not be. Right? The question is, does this basis cover the basis that's generated by this, by the dynamics and my basis set? You need a sufficiently closed, you know, basis set here so that the dynamics stay inside that basis set, so that I can make those, all the terms match. I can tell by people's necks that it's probably a little better if I go back to here. So you can do that for important classes of systems, including the ones that have sines and cosines in them and the ones that have theta dot squareds in them. Okay? But it's simplest to see first just in the lens, through the lens of, let's just say it's, the dynamics are polynomial. Okay? So let's think about polynomial systems. I'll say x dot of x, sometimes I'll write p of x instead of f of x, right? You know, is a polynomial. Right, so it's, again, just a sum of terms like x to some power, x1, x2, whatever, things like this, right? Let's choose v of x to be, I could write it as already in its polynomial form, but I'll just, I'll keep it that way. Phi of x is polynomial. So if phi of x I also choose to be polynomial, okay? And in practice, this is going to be polynomial up to some degree. It's a finite polynomial. It's not an arbitrary degree. Okay, if phi of x is polynomial, then great things happen, right? Partial phi of partial x is polynomial. And partial phi partial x f of x is polynomial. So if I choose my basis function well enough, if I choose some second basis, phi2 of x is a second basis that's also polynomial, up to the degree, it has to be polynomial of the same complexity of this, right? With matching degrees I'll make that a little bit more precise, but this will get the point, okay? Then I could say, I could start in the class of polynomials, if I just enumerate all of the possible polynomials up to degree, the largest degree here, then I can just say the coefficients of these polynomials need to match. And I can start playing the same game I played with the matrix P of x. This is a super powerful idea. It leads this trick together with that closure of the polynomials is sums of squares programming, sums of squares optimization. It has deep ties to algebraic geometry. People know a lot of things about polynomials, okay? Mathematicians know a lot of things about polynomials, and all of those things can be brought to bear on these kind of optimization problems. It's like a really rich topic. But in my shallow treatment of it, what matters is that this gives me a trick for saying if I have some polynomial p of x, and I want to say it's greater than or equal to 0 for all x, then there's a way to do it to say that I'd like p of x to equal m of x transpose big P m of x. I'll use, everybody uses different letters in these. Let me, this, okay. These are play the same roles as my phis did before, but I'm going to call them m now because these are monomials. They're specific choice of phi, which are the monomials, right? A polynomial has, 1 plus 2x squared plus whatever. It's made up of each of these individually is a monomial. In fact, the one we'll have it without the coefficient is the monomial, okay? And Q a positive definite matrix. If I can find a Q with those parameters matching, then I can prove something that the polynomial is greater than or equal to 0 for all x by just a finite number of constraints that are matching my polynomial. And if I know the degree of the terms in P, because I've given P, then I can choose M to be enough monomials to do the matching. So it's not an arbitrary search over M's. I can just write down the ones I know that I need and write the constraints across. Okay, this is called sums of squares optimization. it's a semi-definite program. Right? Those are linear constraints, right? If I just work that out, right? If I just said, for instance, you know, is the matrix 2 minus 4x plus 5x squared greater than or equal to 0 for all real x? This is a question. So that's not immediately obvious that it is. Okay? But if I can put it in here and find a q, how would that work? It's the same way we did before. Right? I'll do it even for a simpler one just so I write less terms. Let's say if I did 1 plus 2x squared. That one is clearly greater than or equal to 0. I could just make a monomial basis. Let's say 1x x squared. I'll make my big Q matrix, Q11, Q12, Q12 again, because it's transpose, Q22. Right, I've got this Q transpose. I have a constraint saying that that matrix has to be positive definite. And then I have a bunch of linear constraints saying what, like Q11, if I multiply this out, Q11, in this case, has to equal 1 to make these coefficients match. What are all the ways I can get an x squared? I could do it from this, you know, times this. I could also do it this times 1, right? So there's a few terms that have to add up to get me, but it's still a linear constraint. It's like Q22 plus 2 Q31 equals 2, okay? There's a bunch of terms that don't appear that have to be 0, but these are all linear constraints to match the coefficient of this polynomial with this parameterized polynomial. Same trick I played before. But if I can just call the solver here, the same way I'm working on the quadratic forms instead of on the complicated nonlinear thing, if I certify that this thing is positive and those equations match, that's a convex optimization, and it can prove for all x, p of x is greater than or equal to 0. Less with me. Ask questions. There's a lot to know about this. You can use it as a user. I think it's just a modeling language where you can now, I gave you this one as a semi-definite program. Now we just have yet another way to call the solver. I could just say, I'd like this to be a sums of squares polynomial like this. And the solver can just take that as a specification, and you can start asking higher level questions about p of x. And that allows you to do crazy things that you would think convex optimization shouldn't be able to do. I've got plenty of examples lined up here. This is a non-convex objective. Just a random set of polynomials, you know, kind of like the one on the MATLAB splash screen, but a little different. It's got a bunch of, this is the contour plot looking down from above. It's got 6 minima. It's called the 6-hump camel. It's a famous nonlinear optimization problem. There are other number of hump camels that are famous. 3-hump camels, pretty famous one. Okay. So you would think that's a non-convex optimization problem. But this is a polynomial. If I want to ask the question, if I want to use these tools, then I can ask questions like, find me a lambda, in fact, maximize lambda subject to that p of x minus lambda is greater than or equal to 0. Did I get that right? Okay. And the way I tell the solver, writing this per se is a hard optimization. But if I relax it to say p of x minus lambda is a sum of squares, that's how we write it, a sum of squares polynomial, this is a semi-definite program, just the way we did on the last screen. And it can solve things like this. It can find the lambda. So what is this saying? This is find me the biggest lambda for which p of x for all x is greater than lambda. That's going to find me the minimum value of that polynomial, that crazy polynomial, if I can solve this. Okay? And to convince you, I just, I sampled a bunch of times to find the smallest possible value. I found the global optima to be this, and sums of squares found it to be this. Right? So it can find the minimum in some pretty complicated problems. It's a powerful tool. There's a lot to know. I cite in the notes, some of the texts if you want to look more. What's the difference between asking for a polynomial to be greater than or equal to 0 versus asking for it to be sums of squares? There's like deep theories talking about that gap. There's cases where there's no gap. In the univariate case, there's no gap if you have only one variable x. But if you have a vector of variables x, there are a few cases where there's no gap. But in general, there are polynomials that are positive for all x, but you cannot find a sums of squares decomposition. But that gap in practice doesn't seem to negatively impact the search for Lyapunov functions. The same way that there's many Lyapunov functions that can prove stability, we can often use sums of squares to find Lyapunov functions to prove stability. Okay, so I know I'm running out of time. Let me put up my last example, and we'll pick up on it again on Thursday to take it further. So the proposal is if you have some x dot equals p of x polynomial, and you come up with a v of x, which is some polynomial again, you can say, I'd like v of x is a sum of squares. You can compute v dot of x. It's still polynomial. I'd say v dot of x negative is a sum of squares. And you can ask the solver, can I find coefficients alpha such that those two things are true? And that can certify the Lyapunov conditions for all x, not just samples, for all x. Right? So again, I'll pick up on them and run with them more next time, but there are many examples. I've got some standard but unusual vector fields that are polynomial lying around. This one I happen to know there's a Lyapunov candidate, which is also a polynomial. I can compute v dot, v partial x times f of x. I can just say, mathematical program, add a sums of squares constraint, v dot. Negative v dot is a sum of squares. Solve, and if it's successful, it verifies my Lyapunov candidate. And to look ahead, you can also search for the parameters of your Lyapunov function. And these problems, when they work, solve just like that. right? And can give you Lyapunov functions. And that's the same, that's the stuff I used for the global analysis of the pendulum. Okay, that's a lot of cool ideas, I think. We'll go back through them and use them farther on Thursday. Okay, see you then.